Okay, I want to talk about lines or affine functions and then eventually get onto derivatives. So to start with this, let's do a little bit of a thought experiment. Okay, we're stuck on a desert island and we're trying to get off, and we don't have a calculator, and I need to calculate the sine of some function so that I don't have to do a whole bunch of guess and checking when I'm building my sail and mast on my little raft to get off this island. Okay, so I need to come up with a good approximation to the sine curve so that when I'm trying to measure these triangles, I can get a pretty good approximation. So let's think about things a little bit. At pi over 2, at pi, 3 pi over 2, and 2 pi, I'm pretty confident that my trig tells me I've got a sine value of 0, 1, 0, negative 1, 0. And that first approximation is pretty good, but it's not quite good enough for me to navigate with if I want to get home. Okay, so I need to augment this approximation a little bit so I can calculate things a little bit more accurately. And I do know that I've got my basic triangles. We'll draw these in blue. I've got my 45, 45, 90, or pi over 4, pi over 4, pi over 2 triangle, and 1, 1, square root of 2. I also have my 30, 60, 90, or pi over 3, pi over 6, 2, 1, square root of 3 triangle. Okay, so this gives me a couple more sine values I can fill in on my curve. I've got pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. And these are going to be 1 over the square root of 2. So I've got a 1, negative 1. I'll make this a little bit bigger here if I can. Okay. There's going to be 1/2. There's going to be 1/2. I've got square root of 3 over 2. And 1 over the square root of 2. Square root of 3 over 2. 1 over the square root of 2. And these are negative values down here. Okay. And I've got pi over 6. And pi over 3. I've got pi over 6 and pi over 3 multiples here, 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 and here. And pi over 6 is a 1/2. This is the next one up, and this is the next one up. And sort of similarly, I've got those guys on the way down. And these guys on the way down further. And these guys on the way back up. Okay. Now, my approximation looks a lot better, right? Kind of got that, and then these straight line approximations. These actually look really pretty good. And if I could draw better, they'd probably look pretty nice. That looks pretty good for a sine curve. Okay, and I've just done straight line approximations, and if I wanted to find a value for I don't know, pi over 18 if I wanted to, or something like that, 7 pi over 18. So I'd find 7 pi over 18 in here. That's a little bit bigger than pi over 3. So I would come up and I'd use this straight line between this value and this value to interpolate the value of the sine. Okay, so interpolation gives a fairly accurate approximation to a function. And now if I put finer and finer line segments together, I'd get a better and better interpolation. Alright, that's kind of where differentiation got its start. At least these are kind of the fundamental ideas for differentiation. So let's see how we can kind of do this to interpolate functions and look at lines and see how they turn into differentiation. Okay. So let's just take a general curve here. I'm just going to call it f of x. Kind of goes off that way, goes off that way. And perhaps I want to approximate values of f near this value here. Well, if I had another value, say here, I could draw the straight line segment between them and interpolate based on this line. Okay, if I had a closer line segment, I could maybe do a little bit better yet and draw interpolated values according to this line. And if I keep doing this and I draw closer and closer secant points, each of these secant lines gets closer and closer to the slope of the function, or gives me a better and better approximation when I'm near this point, this fixed point. The secant line approximations get better as these other points, let me call this P1, P2, PI, as the PI approach, we'll call this guy P. Okay. So let's see how that works. Let's draw or write out the equation for a secant line. So our equation for these secant lines say mi, that's going to be pi minus p divided by, that's the change in the x values, f of pi minus f of p divided by pi minus p. Change in y over change in x. Alright, and so f of x is going to be approximately f of pi plus mi times x minus pi. That's our point slope form for this line. So knowing that we can do better and better with this mi, the closer that pi gets to p, we can take an infinitely close value of pi and figure out sort of the best approximation for this. get a best approximation for f of x near p when pi approaches p infinitely close. I don't want these pi's to change. These are p's. The only thing that changes here, up here, this is our fixed point f of p. That's our fixed point. The only thing that changes is our slope as pi gets closer and closer to p. So we get a best approximation as we get infinitely close to p with these secant lines. And this is where we get our derivative. So f prime at p is going to be the limit as pi gets close to p of f of pi minus f of p divided by pi minus p. This slope gives the best linear approximation at p. And this is what we call the derivative. Okay, so now this definition we're going to have to work with and show that the definition of derivative and all our differentiation rules work out pretty nicely for us. Okay, so definition. Let f mapping r to r. I don't necessarily need r to be where it comes from. Let's take a closed interval a to b. Back into r. Be a function. We set f prime at a point x equal to the limit as t approaches x, f of t minus f of x divided by t minus x. And this is the derivative of f at x when it exists.